New findings on dark energy and its impact on the expanding universe. Using data collected during the first year of the Dark Energy Spectroscopic Instrument Survey (DESI), astronomers have developed a three-dimensional map of the cosmos that contains as many as 6 million galaxies. Through these efforts, researchers have gained insight into the history of the expansion of the universe with the greatest precision ever, providing an unprecedented look at the nature of dark energy and its impact on the large-scale structure of the universe. DESI is an international project involving over 900 scientists from around the world. This is one of the large-scale sky surveys, the aim of which is to map 40 million galaxies and create the largest and most accurate three-dimensional map of the cosmos. DESI is part of the Mayall telescope, which has a mirror diameter of 4 meters and is located on Kitt Peak in Arizona. The instrument enables the study of the history of the expansion of the universe and mysterious dark energy. The instrument began its research in 2021, and astronomers recently reported on an analysis of data collected during its first year of operation. The scientists published the results of their research in a series of articles published on the arXiv preprint server. DESI's enormous capabilities allow researchers to look 11 billion years into the past. Light from distant space objects reaches DESI, allowing scientists to map the cosmos as it was in its youth while also tracking its expansion. But fully understanding the evolution of the universe involves solving one of the greatest cosmological mysteries: determining what dark energy actually is. The DESI data is a huge increase over anything we have collected before, says Kelly Douglas of the University of Rochester. The sample of galaxies and quasars collected in the first year of DESI's work is already 6 times larger than the combined measurements from all previous spectroscopic studies conducted over the last 40 years, he adds. But this is just the beginning. The full dataset, researchers suggest, will enable a closer look at the beginning of our universe, a period when the universe was undergoing rapid exponential expansion. Everything we can see in the world around us, stars, galaxies, flowers or our bodies, constitutes only 5% mass of the universe. This is the so-called baryonic matter. The rest, according to leading cosmological theories, consists of 2 elements: dark matter and dark energy. Their existence is indirectly inferred because these hypothetical substances are invisible, do not emit or reflect light radiation, and are therefore very difficult to detect. But their existence is revealed by the gravitational effects they exert. At least this is how scientists explain anomalies in the rotation of galaxies and the movement of galaxies in clusters. There is too little visible matter to explain the effects occurring in these cases. Dark matter is thought to hold galaxies together and act as the glue that holds them together. However, dark energy, researchers believe, accelerates the expansion of the universe. This means that leading cosmological theories treat dark matter as an element that slows down the expansion of the universe, and dark energy as something that constantly accelerates it. DESI is used to measure the so-called baryon acoustic oscillations, BAOs. In 1970, the future Nobel Prize winner Jim Peebles described a certain phenomenon, putting forward a theory according to which, when the primordial universe still existed, gravity and radiation contributed to the creation of sound waves called baryonic acoustic oscillations. At that stage of its existence, the universe was filled with hot, dense plasma. Gravitational forces and radiation pressure created bubbles, spherical acoustic waves, that moved through the plasma. About 380,000 years after the Big Bang, the universe has cooled enough that this process has stopped. The existing bubbles stopped and froze as areas with a higher density of forming material. However, the universe did not remain static, but began to expand, and with it, also bubbles. Astronomers first found BAO's trace in 2005 while analyzing data on nearby galaxies. In its first year of operation, DESI used nearly 6 million galaxies and quasars to measure the size of BAO and estimate the rate of expansion of the universe, a quantity known as the Hubble constant. BAO is also used to limit the density of dark matter and dark energy. For years, scientists believed that the universe was expanding at a constant rate. But in 1999 it was discovered that the rate of expansion was accelerating. Dark energy is believed to be responsible for the acceleration. Another question that DESI is trying to answer is whether dark energy is a cosmological constant, that is, whether it has a constant value throughout the universe, or whether its properties vary in time and space. DESI's BAO measurements suggest that dark energy may not be a cosmological constant. The DESI instrument has transformed the Mayall telescope into the world's leading space mapping machine, says Pat McCarthy, director of NOAA Lab. The DESI team has set a new standard in the study of large-scale structures of the universe. Data from the first year are just the beginning of efforts to discover the history of the expansion of the universe, he adds. This data allowed astronomers to measure the expansion rate of the universe back to 11 billion years ago, when the universe was only a quarter of its current age. Thanks to DESI's unique ability to map millions of objects both near and far, the BAO distribution could serve as something of a cosmic ruler. By mapping nearby galaxies and distant quasars, astronomers can measure the spread of BAOs over several periods of cosmic history to see how dark energy has behaved. We are incredibly proud of the results obtained in the field of cosmology, says Michael Levi from Lawrence Berkeley National Laboratory, director of DESI. So far we see basic agreement with our best cosmological model, but we also see some potentially interesting differences that may indicate that dark energy evolves over time, he adds. In the most popular cosmological model, the Lambda-CMD model, dark energy is included as a cosmological constant. As Professor Carlos Frenk from the University of Durham, co-author of the study, explains, if dark energy is indeed constant over time, the future of the universe is simple. It will expand forever. But if the clues found on the map come true, it will be questioned. If that happens, we will have to start from scratch, and that means revising our understanding of fundamental physics, our understanding of the Big Bang itself, and our understanding of the long-term projections for the universe, he says, adding that the map's clues left open the possibility that the universe could wait for the Great Collapse. The Big Crunch is a hypothesis that assumes that the expansion of the universe will not last forever. This concept suggests that under the influence of gravity, the expansion of the cosmos will gradually slow down until it stops and the reverse process begins. The universe will begin to contract. Although the expansion history of the universe may be more complex than previously thought, confirmation of the dark energy findings must await the conclusion of the DESI project. As more data becomes available, astronomers will revise their findings. Can prime numbers be predicted? A team of scientists from China and the USA claims that prime numbers can be predicted. Scientists have even developed a system for predicting such numbers, which they call the periodic table of prime numbers. Prime numbers are special. They are only divisible by 1 and themselves. When divided by any other number, they give a fractional result. Prime numbers include 2, 3, 5, 7, 11, 13 and 17. Prime numbers have fascinated mathematicians since ancient times. Over the centuries, scientists have been looking for new, larger prime numbers. One of the most outstanding researchers of these numbers was a French monk from the turn of the 16th and 17th centuries, Marin Mersenne. It is in his honor that large prime numbers are classified as Mersenne numbers. The largest known prime number is the 51st Mersenne prime and has 24,862,048 digits in decimal notation. It is impossible to predict where the next prime number will appear in a sequence of numbers. Mathematicians generally agreed that prime numbers just seem to appear randomly. At least that was the case until recently, because scientists from the City University of Hong Kong, City UHK, and North Carolina State University claim, contrary to what almost every mathematician on Earth will tell you, that prime numbers can be predicted. This is a truly revolutionary achievement in prime number theory, says Wei Kuo of City UHK. Our team has developed a way to accurately and quickly predict when prime numbers will appear, he adds. The result of the team's research is the periodic table of prime numbers, PTP, periodic table of primes, indicating the location of these numbers. PTP provides a platform that makes the study of prime numbers clearer and easier, the authors say in their publication. These discoveries provide answers to questions of interest to the academic community, such as finding the next prime number, factoring an integer, and predicting the total number of primes and twin primes, the researchers explain. If the team's claims are confirmed, it will be a major breakthrough in the modern world. Prime numbers form the basis of many aspects of human activity. One of the most common uses of prime numbers is in data encryption systems. They form the basis of current cryptography and are important when it comes to the security of data transfer. For most applications, the unpredictability of prime numbers is part and parcel of their usefulness. The results and description of the research by Chinese and American mathematicians were published in the Preprint Database, SSRN Electronic Journal. These works have not yet been peer-reviewed.